get a little crazier. Let's figure out the hydrostatic force. So what I've got is, just think of it really simply, it's just another aquarium. Okay? But this time I'm going to submerge a plate that, instead of just being rectangular like it was with the aquarium, I'm going to submerge this plate. Let's do this guy. And I'm going to have this guy be 1 meter deep. So it starts out already 1 meter deep. And it's going to be 1, 2, 3, 4, 5, 6, 7, 8. So we're going to have this height right here be 8. And what it appears though, 1, 2, 3, 4, 5. Let's have this distance here be 5. Okay? Now, I'm going to figure out, this is going to be in water. Let's keep it simple. Let's make these meters so we're not converting meters to feet and feet to meters and using 62.5 pounds per cubic foot and all that other garbage. Okay, it's going to be water. We're submerging it in water, and I want to know what the hydrostatic force is, the total hydrostatic force on this little thing called, which I will refer to later as a lamina. All right, so think of it as a two-dimensional object that's being pushed against the edge of the aquarium. It's a big aquarium, right? The thing looks to be about, I don't know, 30 feet deep, or 10 meters more or less. Okay, so here we go. Same as always. I'm going to change the color. I'm going to give myself a slice of action. That's my slice of action. I'm going to give myself a depth. This is going to be x sub I. If this depth is x sub I, then do you agree that this width of this rectangle is delta x? See how easy that is to think of it in those terms. Now, here's where it gets nastier, because what I need is, I need a width, which I'm going to call this an ith width. Do you see how that width changes the deeper that I go? It's going to get bigger. If I go more shallow, it's going to get less big. It's going to be less wide, right? So what we're going to need is, we're going to need some way to relate w sub I to x sub I. All right? But before we get crazy, let's just write up what we know. I know that the force on that ith little rectangle, this guy right here, is, what do we know? It's the density of water. It's density times volume times the acceleration of gravity. I'll put a g so that you guys see me jumping back and forth. Density of water is 1,000, right? Now the volume. Well, the volume requires that I give it three different dimensions, right? All right, so the width of this thing is going to be w sub I. That's the width of the rectangle. I guess that's the length of the rectangle. Let's keep it simpler. The width is going to be delta x. Notice that I'm just accounting for all three dimensions. And then the depth of it is how deep it is in the water. That's where it's most important, right? Because the deeper we are, the greater force that we have, or that the water exerts on us. So this is x sub I. 1, 2, 3 dimensions, which accounts for that quote-unquote volume that we're not as worried about. And then, of course, times 9.8. You with me? Now, the only trick that I have to do is notice I got x sub I. If I try to take an integral and I've got a w, the dx is going to spit that thing out as a constant, but we know it's not constant. We know it changes. But that's not so bad. Watch. What do I know? I've got similar triangles. Look at that. I've got similar triangles. Now, we got to be really, really careful here, because if we get too crazy, it can get confusing. Do you agree that in this triangle, this little sliver right here is to w sub I as 8 is to 5? So I'm just going to go question mark. Question mark is to 5. Whoops. Question mark is to w sub I. Actually, let's reverse that, because I want to solve for w sub I, right? Let's make our work a little easier. W sub I, so little is to little. So w sub I is to question mark as 5 is to 8. Okay, that's not bad. I'm no longer afraid. However, how am I going to define that? Well, some students say, well, let it be x sub I. No. X sub I is the depth that we go down to the rectangle. Now, I will tell you that there are ways in physics that you might redefine this. You don't have to do it my way. I'm just showing you a way that for me is the most intuitive. I keep it absolutely simple. I let x sub I always be the depth down to the sliver, just so that I'm uniform, so that I don't do anything crazy. Well, if this distance is x sub I, and this distance is 1 meter, then what's the question mark going to be? It's easy now, right? It's just x sub I minus 1, because it's big minus little is x sub I minus 1. So I know that w sub I is to x sub I minus 1 as 5 is to 8, which implies w sub I is 5/8. Ooh, that's a constant that we'll be able to play with. X sub I minus 1. And look at this. So this gives me, I'm going to combine some stuff. I'm going to do 9800 times, now w sub I is 5/8 of x sub I minus 1, that's that guy, times, that's a times by the way, not a minus, times x sub I times delta x. Let's make sure we accounted for everything. Now I'm going to, 100. Okay, w sub I, that's x sub I, sweet, I got it. Now the force is, that's easy, right? All I do is pull out 9800 times 5/8. Those are just constants, so they're along for the ride. Integral, we'll talk about the limits here in just a sec, but for now, do you see that this guy simply becomes x squared minus x dx? And then all I have to do is worry about where are my limits. That's an easy question to answer. Where is the action taking place from and to? Where am I drawing rectangles from and to? Well, I don't draw any rectangles for the first 1 meter because there's no lamina there. There's no plate there, as it were. So I start at 1. This thing is 8 meters long, and I finish where? At 9. It's the integral from 1 to 9. But Ripley, why aren't I integrating from 0 to 8? Well, because if I were integrating from 0 to 8 by the way in which I've defined x sub I, that would imply that this guy were right up at the surface. Saying from 0 to 8 implies that right at the top there's no depth. This one says let's start adding, let's start summing as soon as we're 1 meter deep, and we're not going to finish until we're 9 meters deep. How do I know I'm 9 meters deep? Because the side is 8 meters long. And that's it. That's a pretty cool little problem. Hope you enjoyed that. We got one more little subsection that we're going to deal with in section 6.5, and then thank God we're done with 6.5. But remember, we're taking a really long time on it too. Okay? Hope you enjoyed, and I'll see you in the next section.